Hello friends, welcome back to the course on differential calculus. The limit of a function is a fundamental concept in calculus concerning the behavior of that function near a particular input. In this session, we will study limits informally with a good goal of developing an intuitive feel for the basic ideas. In the next two sessions, we will focus on computational methods and precise definitions. One of the important themes in calculus is the study of motion. To describe the motion of an object, one must specify how fast it is going, and this is done by discussing its speed. A moving body's average speed over a particular time interval, closed interval t0 plus delta t is the amount of distance delta is covered during the time interval divided by the length delta t of the time interval. For example, if a car covers a distance 120 km in 2 hours, we say that the average speed of the car is 120 km upon 2 hours equal to 60 km per hour. But we know that even if a car has an average speed of 60 km per hour at a particular time, say at 5 minutes and at 10 minutes, the speed that speedometer of the car shows may be different. Speedometer shows instantaneous speed at a particular time. Suppose the distance covered by a moving car from its initial position after t second is given by s of t meters, where s of t is a function of time t. Then the distance travel at a time t0 second is s of t0 meters, and the distance travel at time t0 plus delta t second is s of t0 plus delta t meters. And so, the distance covered during the time interval closed interval t0 plus delta t is the difference of distance covered in t0 plus delta t seconds with that in t0 second. That is the value s of t0 plus delta t minus s of t0. Thus, the average speed over the time interval closed interval t0 plus delta t is given by delta s upon delta t equal to distance covered during the time interval upon length of the time interval equal to s of t0 plus delta t minus s of t0 upon delta t. If we decrease the length delta t of the time interval indefinitely till in the limit delta t approaches 0 and follow the average delta s upon delta t all through the process, delta s similarly decreases indefinitely and ultimately approaches 0, but delta s upon delta t does not, thereby present us with the meaningless symbol 0 upon 0, but with a definite limiting value, which is the required instantaneous speed at a time t0. Let us consider an example. Suppose a car is driven such that after t seconds where 0 less than or equal to t less than or equal to 12, it is s of t equal to 1.5 t square meters from its initial position. That is, the distance covered after t second is given by s of t equal to 1.5 t square meter, 0 less than or equal to t less than or equal to 12. The average speed of the car over the interval closed interval 6-12 is delta s upon delta t equal to distance covered in 12 second minus distance covered in 6 second upon length of the time interval equal to s of 12 minus s of 6 upon 12 minus 6 equal to 1.5 into 12 square minus 1.5 into 6 square upon 6 equal to 27 meter per second. Similarly, the average speed over the short time interval closed interval 6 plus h is obtained as follows. Delta s upon delta t equal to s into 6 plus h minus s of 6 upon 6 plus h minus 6 equal to 1.5 into 6 plus h whole square minus 1.5 into 6 square upon h. Algebraic simplification yields that the average speed over the time interval closed interval 6 plus h is delta s upon delta t equal to 1.5 into 12 h plus h square upon h equal to 18 plus 1.5 h. Using the equation 1, we have the following table. The table shows that when h approaches 0, that is when delta t approaches 0, the average speed over the time interval closed interval 6 plus h seems to approach 18. We say that instantaneous speed at time t equal to 6 is 18 meter per second or 64.8 kilometer per hour, which the speedometer of the car shows at 6 seconds. We denote it by writing limit of delta s upon h as h approaches 0 equal to limit of delta s upon delta t as delta t approaches 0 equal to 18 meter per second. This is also justified by equation 1 by letting h approaches 0. Informal definition of limit using Graph function. In order to see the behavior of a function y equal to f of x when x approaches a fixed point, say c, we can use the numerical table values as we did in the previous example. Another way is to use the graph of the function to get an intuitive idea of limit of a function when x approaches a fixed point. Let us discuss the behavior of the function y equal to x plus 1 near x equal to 1. We do this using the graph of y equal to x plus 1. It can be seen that when x approaches 1 along the x axis from the right side, the corresponding point on the graph approaches the point ordered by a 1, 2. Simultaneously, values of y equal to x plus 1 approaches 2 along the y axis. We say that x plus 1 approaches 2 as x approaches 1 from the right side. 2 is called the right hand limit of x plus 1 when x equal to 1 or when x approaches 1. We denote it by writing limit of x plus 1 as x approaches 1 from the right is 2. Also, we observe that when x approaches 1 along the x axis from the left side, the corresponding point on the graph approaches the point ordered by a 1, 2. Simultaneously, values of y equal to x plus 1 approaches 2 along the y axis. We say that x plus 1 approaches 2 as x approaches 1 from the left side. 2 is called the left hand limit of x plus 1 when x equal to 1 or when x approaches 1. We denote it by limit of x plus 1 as x approaches 1 from the left is 2. Thus, when x approaches 1 from both sides along the x axis, the corresponding values of y equal to x plus 1 approaches 2 along the y axis. We call 2 the two-sided limit or simply limit of x plus 1 at x equal to 1 or when x approaches 1. We write this limit of x plus 1 as x approaches 1 equal to 2. Getting intuition from the above example, figure shows that f of x approaches the two-side limit L as x approaches c if and only if f of x approaches L as x approaches c from the left as well as from the right. Informally, we define limit as follows. If f of x can be made as close as we like to the number L by taking values of x sufficiently close to c but not equal to c from both the left and right sides of c, then we write limit of f of x as x approaches c is L, which is read limit or two-sided limit of f of x as x approaches c is L or f of x approaches L as x approaches c. As an example, from the graph of the function f of x equal to x square, it can be seen that whenever x gets closer and closer to 2 along the x axis from either side, the corresponding values f of x equal to x square gets closer and closer to 4 along y axis. That is, f of x equal to x square can be made as close as we like to the number 4 by taking values of x sufficiently close to 2. Hence, limit of f of x as x approaches 2 equal to limit of x square as x approaches 2 is 4. As another example, let g be given by the formula g of x equal to x square minus 1 upon x minus 1 whenever the formula makes sense. Clearly, the natural domain of the given function is the set of real numbers except 1. For any x not equal to 1, we have x minus 1 not equal to 0 and hence division by x minus 1 is possible, and we have the simplification. G of x equal to x minus 1 into x plus 1 upon x minus 1 equal to x plus 1 for x not equal to 1. Thus, the graph of G is the line y equal to x plus 1 with the point ordered pair 1 2 that corresponds to x equal to 1 is removed, which is indicated by a hole as in the figure. Even though g of 1 is not defined, it can be seen that when x approaches 1 from both sides along the x axis, the corresponding points on the graph approaches the hole ordered pair 1 2 and simultaneously the corresponding g of x values approaches 2 along the y axis. We denote this by writing limit of g of x as x approaches 1 equal to limit of x square minus 1 upon x minus 1 as x approaches 1 is 2. Here we note that even if g is not defined at x equal to 1, the behavior of g near x equal to 1 is that g values approaches 2. As another example, consider the function h of x equal to sin x upon x, which is defined for all real number except x equal to 0. Let us examine the behavior of sin x upon x when x approaches 0. We plot a set of table values for x and then find the corresponding values of the function. From the numerical values in the table or from the graph of sin x upon x, it can be seen that when x approaches 0 from both sides along the x axis, the corresponding sin x upon x values approaches 1 along the y axis. We denote this by writing limit of sin x upon x as x approaches 0 is 1. That is, even though sin x upon x is not defined at 0, its limit exists when x approaches 0. Limit may not always exist. In contrast with the previous examples, limit of a function need not exist always. To see this, let us consider the function f of x equal to x upon absolute value of x, which is defined at every point except x equal to 0. Since absolute value of x equal to negative x when x less than 0 and positive x when x greater than 0, the given function f can be represented in the form f of x equal to negative 1 when x less than 0 and positive 1 when x greater than 0, and its graph is given in figure. Whenever x approaches 0 along the x axis from the left, f of x approaches negative 1 and hence limit of f of x as x approaches 0 from left is negative 1. Then negative 1 is the left hand limit at 0. As x approaches 0 along the x axis from the right, f of x approaches positive 1 and so limit of f of x as x approaches 0 from right is 1. Thus, 1 is the right hand limit of 0. As the left hand and right hand limits are different, limit of f of x as x approaches 0 does not exist. Limit of function at endpoints. Let f of x be defined on any of the interval open interval a b, closed interval a b, left open right closed interval a b and right open left closed interval a b where a less than b. Then limit of f of x as x approaches a from the right may or not exist, but limit of f of x as x approaches a from left does not exist as the function is not defined to the left of x equal to a. Hence, limit of f of x as x approaches a is also does not exist. Similarly, limit of f of x as x approaches b from left may or not exist, but limit of f of x as x approaches b from right does not exist as the function is not defined to the right of x equal to b. Hence, limit of f of x as x approaches b also does not exist. As an illustration, consider the piecewise defined function whose graph is given in figure. Referring the graph, it can be seen that limit of f of x as x approaches 0 from right is 1, limit of f of x as x approaches 0 from left does not exist as the function is not defined to the left of x equal to 0. Hence, limit of f of x as x approaches 0 also does not exist. We also have limit of f of x as x approaches 1 from the left is 0 and limit of f of x as x approaches 1 from the right is 1. As the right hand left hand limits are not equal, limit of f of x as x approaches 1 does not exist. Also, limit of f of x as x approaches 2 from left is 1 and limit of f of x as x approaches 2 from right is 1. Thus, limit of f of x as x approaches 2 is 1, even though f of 2 equal to 2. It can be observed that limit of f of x as x approaches 3 from left equal to limit of f of x as x approaches 3 from right equal to limit of f of x as x approaches 3 equal to f of 3 equal to 2. We also have limit of f of x as x approaches 4 from left is 1 even though f of 4 not equal to 1. Limit of f of x as x approaches 4 from right does not exist as the function is not defined to the right of x equal to 4, and limit of f of x as x approaches 4 do not exist as the function is not defined to the right of x equal to 4. At every other point a in closed interval 0 4, f of x has a limit f of a. Infinite limits. As another example, let us consider the behavior of the function f of x equal to 1 upon x for values of x near 0. It is evident from the graph that as x values are taken closer and closer to 0 from the right, that is along the positive x axis, the corresponding values of f of x equal to 1 upon x are positive and increase without bound. We describe this limiting behavior by writing limit of 1 upon x as x approaches 0 from right is positive infinity. As there is no finite real number L such that limit of 1 upon x as x approaches 0 from right is L. We say that limit of 1 upon x as x approaches 0 from right fail to exist. That is, right hand limit does not exist when x approaches 0. Also, as x values are taken closer and closer to 0 from the left, that is along the negative x axis, the corresponding values of f of x equal to 1 upon x are negative and decrease without bound. We describe this by limiting behavior by writing limit of 1 upon x as x approaches 0 from left is negative infinity. As there is no finite real number L such that limit of 1 upon x as x approaches 0 from left is L, we say that limit of 1 upon x as x approaches 0 from left fail to exist. That is, left hand limit does not exist when x approaches 0. As neither the left hand nor the right hand limit exists as x approaches 0, we conclude that limit of 1 upon x as x approaches 0 does not exist. As another example, for the function f of x equal to 1 upon x minus 2 whole square, we have limit of 1 upon x minus 2 whole square as x approaches 2 from right is positive infinity, and limit of 1 upon x minus 2 whole square as x approaches 2 from left is positive infinity. Then we write limit of 1 upon x minus 2 whole square as x approaches 2 is positive infinity. Here also we conclude that limit of 1 upon x minus 2 whole square as x approaches 2 does not exist. As another example, for the function f of x equal to negative 1 upon x minus 2 whole square, we have limit of negative 1 upon x minus 2 whole square as x approaches 2 from the left is negative infinity, and limit of negative 1 upon x minus 2 whole square as x approaches 2 from the right is negative infinity. Then we write limit of negative 1 upon x minus 2 whole square as x approaches 2 is negative infinity. Here also limit of negative 1 upon x minus 2 whole square as x approaches 2 does not exist. Sampling pitfalls, table values may lead to wrong conclusions. In the previous examples, we have used either graphs or numerical tables to examine whether limit exists at a point or not. We are now going to see that numerical table can sometimes lead to incorrect conclusion about limits because of round off error or because the sample values chosen do not reveal the true limiting behavior. As an example, let us examine whether limit of sin of pi upon x as x approaches 0 exists or not. We construct a numerical table showing some x values and the corresponding f of x equal to sin of pi upon x values. The numerical table gives us a conclusion that limit of sin of pi upon x as x approaches 0 is 0. We claim that this conclusion is false. To see that conclusion from the table is false, let us consider the graph of the function f of x equal to sin of pi upon x, where x not equal to 0. The graph reveals that the value of f oscillates between -1 and +1 with increasing rapidly as x approaches 0, and hence the function's values do not approach a limit value. That is, limit of sin of pi upon x as x approaches 0 does not exist. This shows that the conclusion from the numerical table is false. The data in the numerical table deceived us because the sample x values selected all happen to be x intercepts for f of x. As another example, for the function f of x equal to square root of x square plus 4 minus 2 upon x square. The following table will mislead us to conclude that limit of square root of x square plus 4 minus 2 upon x square as x approaches 0 is 0, which is wrong. Using some method, we will see in the coming session that limit of square root of x square plus 4 minus 2 upon x square as x approaches 0 is 1 upon 4 is the right answer. The wrong conclusion obtained from the table values is due to the following fact. For x very close to 0, square root of x square plus 4 is very close to 2. When subtracting two numbers from nearly equal values on the calculator, a loss of significant digit may occur due to round off error. The last two example points out the need for having alternative methods with a strong theoretical support for finding limits. For that, we need formal definition of limit of function, and that in the context of next session. Let us summarize this session. In this session, we have introduced the concept of limit of a function intuitively using numerical tables and graphs of function. A number of examples in this regard have been discussed. Also, we have seen examples showing pitfalls in depending on numerical tables and graphs that may lead to wrong conclusions. This is due to the fact that we have not yet given the precise definition of limit of a function. We will given the precise definition in the next session. Thank you for watching this session. See you in the next session. Bye.